and I wanted to tell you why and how it all came about. Because the curriculum has been studied a lot in the last few days or the last few months, and I I was told that we had to eliminate any we had to eliminate any of the concentrations that weren't 15 hours in length, and we only had three courses, and that's 12 hours, and we couldn't get another course in. So basically, we had to do something. And if you look here in the junior senior year, there's three tech elective, tech elective, and there's only three slots for those as you see this. So that's 12 hours, and that wasn't enough to give us 15 hours for concentration. But we were told by the provost yesterday, or the day before yesterday, that we were grandfathered in because we had established what we had before they brought that 15-hour requirement in. So I went and asked the chairman of electrical, who was our new boss, if that would be okay, and he said yes, and we would give it a new name, slightly different, and we would reestablish it. So the concentration will be called mechatronics and robotics. So if you want to do that, it'll still be available, and that'll be on your diploma. Anyway, the other thing about it is that up here, you do 10-10 and 10-20. Now, you've already done 10-10 and 10-20, but in the future, not necessarily next year, but the year after that, EECS 2300 is equal to 10-10 plus 10-20. So they teach it all in one semester. And I think that you understand after you've gone through this that you could probably have squished it into one semester, because I pretty well did. Okay, so I've taught other things at the end, but basically you could have taken it all in one semester. So what we're going to offer to people down the road is a social science or humanities, something up here just to get them through. And then this course would be EECS 2300, or we will still offer it this way. So we'll either do it this way, or you'll have the EECS 2300 here, and then you go through the rest of your curriculum. So you can't do that. But I'm telling you that if you wanted to decide that you wanted to get into the EECS program, these two are equal to that. Okay? They're equal in every way. And you should, if you ever wanted to do the transfer, you could do the transfer because they are equal. You might be a little bit shy of something, whatever they're doing over here. I don't know what they're doing over here, but basically, now the reason we're going to have to offer these forever is because there is something called a tag requirement in the state of Ohio. So every two-year school in the state of Ohio that has an electrical program offers it this way, or they should, because it's the law. So they offer it as 2 4-hour courses, and they're equivalent to our two courses, so that you can take this anywhere in the state of Ohio, this course and this course, and you can transfer them in as this course and this course here. It's called Transfer Agreement Guarantee, TAG, okay? So that's a law we have to abide by. But what I'm telling you is that down the road, we're going to give you the option of a 4th course there. So I'm just giving you all this information because I want you to know that I've been trying to get this problem of what to do about the concentrations and all that kind of stuff kind of, okay. Now, what does this concentration mean? Well, it means you can take It's a potpourri, really, is what it's going to mean. You can have from the list of the mechanical side, or from the electrical side, about anything you want. So there's going to be a shopping list of 3 courses on this side, 3 or 4 courses on this side, and you can pick any of those that you want to give you this. So it's pretty much the same as our standard curriculum, with the exception that if you wanted to say this, you just have to apply for it. That makes sense? It'll give you the option for your diploma to say that. So hopefully you understand. We've been through the mill to get this done, but with the moving into the EECS department and all these other curriculum things that have come up, we just basically have had to kind of stand on our head for a little while because they made us stand on our head. But with all that said, I think we try to protect you as best we can, and I think that's what we've done. So this will be back reestablished, and you can get back in it if you want. So that's how it's going to happen. Okay. So that's another brother. Now this is the other side of this thing. Okay, so let's go back and look at where we're at today and what we got to do. And what keeps me up at night is thinking about, I've got 4 courses like this, and what course do I have to write a test for today, and what course do I have to write a test for tomorrow, and which course do I have to have graded by tomorrow in order to get through the next 2 weeks? Because the next 2 weeks are going to be what? Final week of coursework and finals week. So getting through the next 2 weeks is my goal, living through until May 1st, at which point in time I basically do that. And anyway, any questions about that? So let's look and see where we're at. We're right here right now. We're at the 16th, right? Can everybody see that? Any questions about where we're at? We're going to finish chapter 4. We're going to work some of these problems. I'm going to go back and work number 10 and 11 from chapter 3 because I messed those up. On Tuesday, we're going to have a review for our exam 2. On Thursday of next week, we're going to have our exam 2 in class. On the 28th, we're going to have our final exam, 8 to 10 a.m. in class, comprehensive. That means from everywhere to anywhere. That means the whole gamut is whatever. No surprises. Usually I just look at your hour exams and take the questions off of the hour exam that were the most missed. Lab 9, build a circuit to control the cylinder and the back and forth motion. That counts 3 labs. So that's 60 points. Lab 10, and you have to turn in with that a sheet, okay? You guys have already showed me, but you need to turn in a sheet that shows kind of what you did. Just one page, 2 pages, it doesn't matter, but you got to have something handed in for that. The video is fine. If you take a video showing it going back and forth with your circuit, excellent. That would work for me. If you don't do a video, drag me up there. Are they here? Come here with us. Come here with us. And I'll come and I'll look at it and say, good job. But anyway, that's where we're at. Lab 11, prove to me that you have cleaned up your area. All the stuff that's in that lab having to do with your particular blessed going back and forth cylinder. Clean it up, make it look nice, take the wires off, get another 20 points. I'm tired of taking those apart. I'm sorry. I've done that for the last 3 years, and with the number of people that are involved, it pays me to actually give you a lab to do that, okay? So, any questions, any comments, any thoughts? Everybody's fine with all this stuff, and you kind of understand what I just said. If you don't understand what I just said, or you have questions, see me, or listen to the video again. But basically, I think I've explained myself. If everybody kind of got it, maybe that's good. Okay, so this is up to date and it's on the website. This is a clean syllabus, as they say right now. This is a pretty straightforward syllabus. I've got all your stuff graded that has been handed into me, and in general, you did a really good job on the conduit layouts. That's a that's a heavy lift for one quiz grade, but so be it. You get something out of it, hopefully, and you've had to look at the electric code quite a while to figure out how to do some of the stuff. Good. That's a that's a good exercise. Not easy, doable. Okay. So let's go back to chapter 3 and those two problems that I messed up, all right? So this is the chapter 3 problems that I kind of didn't do. So these are two problems that you'll probably never see on a test because I messed them up, but I don't want to, basically say how bad I messed them up, but I messed them up. And basically, if you go back and look at the section, basically what this is, this and this is like a power supply that boosts you up to a value, and that value is the value of the peak of this guy right here, and that gives you a let's just look at that section of the what it does. It's not anything magical. It just is not. It's kind of strange, and so these are called clampers. All right. It adds a DC offset to an AC signal in such a way that the resulting voltage is unipolar. Okay, so it basically is it you want something like this. And this would be the result of that. Let me just show you this. So this is the offset. So it pushes it from 0 up to the value of the the peak value plus an offset. And here the offset is 5 volts. Okay. So this would be the peak of this plus this offset is how far this is pushed up. And that would be, here is my peak, and this would be my offset. So whatever this is, minus the 0.7 volts, is my offset. So you're pushing the middle of that signal from the peak of this signal plus the offset, which is from the 5 volts would be the 5 volt DC offset. 5.7 volts minus 0.7 volts is the offset. And that's how this is done. There's nothing magical about it. It's kind of a dumb circuit. I'll never ask you one on a test. If you remember this is called a clamper circuit. That's all it does. As long as the time constant of the RC is much greater than the frequency of the circuit. If it's not, it doesn't work. Okay? But as long as the RC of this is greater than the frequency of this by a factor of 10, you get this offset. And that's all this is. And I'm not going to cover it any more in depth, but that's what it is. 10 and 11. If you want to work them, you can. If you want to skip them, I'm not going to take off. I'll give you credit for them, those 11 problems. Okay, so that is a homework assignment that is due. If you didn't look at the homework assignments, that is part of your assignments to do. And let's go back and look at that. So you've got homework assignments here. And we've worked most of these questions, so we're not giving you something that you haven't seen, okay? So out of chapter 2, page 56, 1 through 10, and we worked most of those. Out of chapter 3, 1 through 11, and I just told you about 10 and 11 that you don't have to do them, but if you do, you can. If you don't, you don't have, it doesn't matter. 10 and 11, I'm not going to worry about. Chapter 4, 1 through 13, which I'm going to hopefully work as we speak today. So that's my goal, is to get through those questions today. Chapter 4. Any questions, any comments? And that wraps it up. That's our goal, is to get through chapter 4. Questions? All right. So, what's that? Sure. Say again, I didn't get that. I still didn't understand. Say, what about it? A study sheet? Yeah, I'm going to talk. Well, I'm not going to put out a study sheet, but I'm going to talk you through on Tuesday. I'm not going to have it written on Tuesday, but I'm going to have in my head the kind of problems that'll be on it, and I'll go through those review with you on Tuesday. So the review, if you're not here on Tuesday, listen to the video, because the review, not for the final. The final exam, okay, the review on Tuesday will be for the third exam, or for the second exam. There will be no review for the final, except for look at your 2-hour exams. Study them good. Because usually what I do is I take the problems off of those hour exams, and I don't vary from that very much at all. So if you want to understand, and also the problems that were on the hour exam that were the most missed, okay? And I can tell you from our exam 1 what the problems were that were the most missed. And I thought about having an answer sheet for the second hour exam. Okay, it looks like 1 through 4 and 7 through 10 were the most missed. 5 and 6 were the least missed. So if I were you, I would study problems 1 through 4 and 7 through 10 off of our exam 1. Oh yeah, you can bring your 4 sheets or 5 sheets, study sheets. Yeah, yep. 1 through 4 and 7 through 10 from the first hour exam were the ones that were missed. And you're only going to get 10 questions, so there's a good possibility that 5 of the 10 will be 1 through 4 and 5 through, and 7 through 10. Those are the ones that were missed. And second hour exam, if you want to come by and see your test, I should have it graded by Monday. So you can pick it up on Monday of finals week, okay? And you can see me on Monday, and I should have it available. So you can see what you missed, and I'll know then what the problems were that were the most missed on that one. So basically, honest to goodness, the final exam is not meant to be new stuff. It's to be old stuff again. And usually it's the stuff, here's the stuff that you missed. Now did you get it? Okay, so 1 through 4, 7 through 10 out of our exam 1. We'll see what our exam 2 is like. And 10 questions makes it easy to grade. 10 times 10 is 100, so 10 points apiece. Number answers, typically, numeric answers. Other than that, I know everybody grimaces thinking about a final. Oh yeah, it's tough, but usually finals are not that hard if you know if you've studied or if you know this stuff, or it gives you another chance. It gives you another shot, and most people take advantage of it. And by that time, they figured me out, or they kind of know a little bit about what it was, and I I think you'll find that I'm very fair. But on the other hand, I want you to learn this stuff. Okay, so that's those questions at the end of chapter 3. Now we're into chapter 4, and we need to get these problems done at the end of chapter 4. So I'm basically going to go down there and work them. And by the way, is anybody thanking us a little bit that we actually get into this chapter or this stuff on transistors because you're doing a lab with a transistor? Does that make you feel any better, or maybe a little bit, hopefully? Maybe a little bit? Hopefully. I don't know. So these are the questions at the end of chapter 4. So I do not remember the formula between alpha and beta. So I got to go back and look. Sorry about that. But I know this is rudimentary, but I should know, but I don't. Okay, so let's look at the relationship between alpha and beta in the formulas. Here, someplace, okay, so alpha is equal to IC over IE. Beta is equal to IC over IB. So alpha is equal to beta over beta plus 1. Beta is equal to alpha over 1 minus alpha. So that's your equations. You never use alpha, by the way. You do use beta. Let's go back and look at the questions at the end of chapter 4. Okay. So beta, if alpha is equal to 0.99, so 0.99 is equal to beta over beta plus 1. So 0.99 beta plus 0.99 is equal to beta. And that would be 0.99 is equal to 0.01 beta. Beta is equal to 99. Does everybody agree with that? Or 100? Okay, so that's number 1. Number 2, alpha, if beta is equal to 200, so here's alpha, so it's alpha is equal to 200 over 201, or what? 0.995? Yep, 0.995. That's number 2. All right. Now here is the starting of this here's where it really starts. And these are not hard questions. These just kind of flow. But you have to start asking yourself now, what are they at? By the way, what are you learning from the putting the lab together for the reciprocating motor, the reciprocating device? What's the main thing that you have to do there? You have to know what to do first. Okay, you got to build the circuits that do the time delay off of the limit switches. You got to build those first, and you got to tie those into your circuit that does the direction DIR. And once you got that done, then you can build the circuit that flips the context of the relay. You got to do it in order, or it doesn't work. And that's part of discovering how to do a project, like how you build things. You have to do them in an orderly way. I wrote a program at the end of my programming career as an engineer for a company in LaPorte, Indiana, and it was the whole line. And usually you have to program things from the downstream side to the upstream side. And that's what I had to do. I had to program all the things that were going on downstream because the upstream things needed the information from the downstream. In order for me to get that, I had to have it already programmed to know what the variables were. So I programmed from the back side, from the downstream side to the front or the upstream side of this process. I wrote the whole thing. Unfortunately, I didn't get a chance to start it up because by that time I was getting pressured from the university to not do any more work like that. I finally said I can't do any more of it, and I resigned from them, and that was the end of that. But I did write the whole line, the program for the whole line, and it was from the back side to the front side. And if you think about it, you have to have the downstream stuff in order to do the final stuff, and you have to do it in order, or it won't work. Anyway, determine the currents for the circuit for VBB is 5 volts, VCC is 20 volts, RB is 200K, RC is 2K, and beta of 100. Okay, so this is number 3. This is 5. This is RB is 200K. And usually it's drawn like this. It's drawn with the VCC up here and then resistance. So this would be VCC is 20 volts and RC is 2K, and then you come down to ground. So this is how that's done. Okay, so determine the currents. So if and beta is 100. So what's the drop of the voltage across the from here to here? VBE. It's 0.7 volts. So what's the voltage? What's the voltage across the 200K? The voltage across the 200K is it's IB is equal to what? 5 minus 0.7, or 4.3 divided by 200K. Okay, and that gives me my current through my IB, right? So it's 4.3 divided by 200, or 21.5 micro amps. Okay. Any questions about that? So that's the little one. Now, what is beta? Beta is equal to 100. So what is IC is equal to what? 21.5 times 10 to the minus 6 times 100, or what? 0.215 milliamps, right? Or is that? No, it's 2.15 milliamps. 2.15 milliamps. Okay. So there we go. That's my IC. What is IE? It's IE is this plus this, but we really don't care. Now, what is the question? What determine the currents? Okay, that's 2.15 milliamps. And that's it. Now, here the next one is determine the voltages for the circuit. Okay, first one is determine the currents, and we did. Now we're going to go back and we're going to change the only thing we change is the beta. So problem number 4, okay, so IB is 21.5, IC is this, IE is the sum of the two, so it would be 2.15 plus 0.215, 0.0215, and that's IB plus IC. Okay, that's that one. Anyway, that's all that is. Now, what about number 4? The voltages. Okay, so this one's a little different. Still got the 5 volts, you still got the VCC of 220, you got the 200K, and you've got everything the same except the beta is 200. So IB is the same microamps, but IC is equal to what? Double this, right? 43 microamps. So now see what else. Okay, so if that's the case, what would be the voltages? Okay, so now we've got to look at the voltage drop across this 2K resistor, and that would be what? It's 43 milliamps. Okay, so V2K is equal to what? 43 times 2, or forty 43 milliamps times 2 is 86. It's 86 volts. But you can't have 86 volts because you can't get above 20. So basically, what have we done here? We've saturated this guy, haven't we? Determine the transistor voltages for the circuit if VBB is 5 volts, VCC is 20 volts, RB is 200K, and RC is 2K, beta is 200. You come up with this current of 43 milliamps, microamps, but you can't have 43 microamps because you can't go above what? 20 volts divided by 2K is what? 10 milliamps. So you can't have 43 milliamps. So this is one of those cases where you ran into the wall and you just can't go any further than that. So basically, this is your maximum is 10 milliamps. Everybody follow that? you cannot exceed 10 milliamps in that circuit. You can't have more than 10 milliamps flowing down through there. So this leading you along by this beta of 200, this basically smacks you into that wall, and you can't go beyond 10 milliamps. Does everybody follow that? You can't get blood from a tournament, you can't get more than 10 milliamps from that circuit. So this is, you can't do it. You run into the wall and you stick. You're saturated. So you're saturated at 10, you can't go to 43. You can't do it. Any questions about that? What is the answer? Do they have answers to this? Because that's exactly how that's done. Anyway, okay, let's go back. That's all that is. Okay, now number 5. Determine the LED current. So this one is one where the LED is taking up some of the voltage. It soaks up some of the voltage, 2.1 volts. RB is a certain voltage, a certain something, and you've got all this stuff. If logic input is 5 volts, okay, so this is the same thing. You've got 5 volts, and you've got RB of 3.6K. Okay. 3.6K ohms. You got the VCC is 5 volts. And you have an RC of 270 ohms. And you have your LED in there, okay, which soaks up 2.1 volts. All right, so now let's see what we got. You got a beta of 100. Determine the LED current. Okay, so here we have to ask the question, is this going to be forward biased or not? So basically, if it is, and it is because this is greater than 0.7 volts. So if this is on, and which it is, we basically can say, okay, 5 minus 2.5 minus 2.1 volts is equal to 2.9 volts. And then it's divided by 270 ohms. That gives me my maximum current. Just what? Beta it doesn't really matter what beta is. 2.9 divided by 270 is equal to 10.7 milliamps. 2.9 volts divided by 270 ohms is 10.7 milliamps flowing through that LED. Okay, that's all that is. You can ignore the beta because you get the current here and you multiply it by that. You probably are in saturation because it's probably going to be more than the value that it's turned. This is turned on. This is like a switch that's closed, and this would be 0.7 between here and here, and it should be about 0 between here and here. So that basically says this flows like a switch. This is closed. Okay, enough on number 5. These are not necessarily easy, but the steps to getting them are pretty straightforward. Number 6, determine the current through if V logic is 0 volts. Now they basically turned it off. And if it is off, number 6, this would be, there would be no voltage across this because this switch would be turned off. LED is 2.1, RB is 3.6, blah, 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 and all that kind of stuff. So the difference here is they've turned this to 0 volts, which 0 is less than 0.7, there's not going to be any flow. Therefore, if there's no flow, this is like an off switch. So this would be 0 volts here. Excuse me. This would be no current, and this would be 5 volts here, and be, so basically, number 6, the LED current is equal to 0. Because the reason for it is because the logic here is 0. This voltage, this logic voltage right here is 0. If this is less than 0.7, this is 0.7 from here to here. If this is less than 0.7, there is no flow of current in the RB, and therefore it's off, the switch is off. Number 7, determine the LED current in the circuit of 4.28 if V logic is 5, VEE is 5, et cetera, et cetera, et cetera. So now we're talking the same thing, only reversed. Okay, this one I am not as good at. I have to skip that one for right now. Sorry about that, but I'm going to have to, let me go back and look, because I think I can do this pretty quickly, but I have not reviewed this recently. Okay, for this circuit right here, okay, so this right here says a logic low, turn on the LED, and a logic high, turn it off. So this would be the opposite, okay? So that's all this is, and that's what I thought. So let's go back to number 7. Okay, so a logic low, and that's not the case here, the logic is high. So the current here would be 0. There is no flow in number 7. So this would be a case where the logic is high, I is equal to 0 in my RC, in my LED. It's off, because if the logic here is high in this circuit, it's backwards. Number 8. Determine the LED current of the circuit in 428 if the voltage is low. Okay, so this one would be the opposite. All right, so in this case, if it's low, the circuit is on, and LED is 2.2 volts, RB is 2.7K, you don't care about that, RC is 220 ohms. So in this case, 5 volts minus 2.2 volts, the drop across the LED, divided by RC, or 220 ohms, is equal to my current through my RC. Okay, so that's your current. When the voltage is off, then this one flows. Okay, that's all this is. Not easy, but that's exactly what it does. Okay, so now we're going to go down to number 9. We're almost done with these. There's only 13 of them. We'll be done in a few minutes. Number 9, determine the LED current of the circuit of figure 429. Okay, so in this case, VCC is 10 volts. The LED is 2.3. RE is 270, and beta is equal to 200. Okay, so V logic is 3.6, which is above 0.7, so it is on. So if this circuit is on, we have flow, and we have flow from 10 minus 2.3, so that's our total voltage from here to here is 10, but we take away 2.3, and then we divide that by RE of 270, and that gives us my IC. The LED current would be 10 minus 2.3 divided by 270. Approximately. There's a little bit, you're a little bit off, but it's close. 10 minus 2.3. $28.5 milliamps. Number 9. Number 10. Determine of LED current in the circuit if V logic is 0. If V logic is 0, the circuit is off, the switch is off. So there is no current flow. So the LED is off. Okay, so number 10, IC, said the blind man, IC is equal to 0. Circuit is off. If the voltage at this point is less than 0.7, the switch is off. Okay? Simple. And you did that, or you're doing that in your circuit for your lab. Okay, number 11. Using the blah, blah, blah data sheet, determine, okay, I'm going to let you do that one. And you can figure that one out. Using the data sheet, you can do that one. Using the data sheet, you can do that one. Okay, just read it off the data sheet and you're done. Look at the data sheet. Find out those variables and you're all set. That's not a big deal. Read the data sheet is in the book, but again, you just look on the data sheet and find those variables. Have a thorough review. A couple of these problems might be one of these problems on the test. It'll be simple. It'll be like either number 9 or number 3, number 4, that type of thing. Okay, so on Tuesday, a thorough review. You got some problems to hand in from chapter 2, 3, and 4 of this book. Whatever I do in this stuff with the diodes and the transistors will be easy. It will not be hard at all. It will be very easy. And I'll review pretty much what I'll ask you from chapter 3 and chapter 4. Will we go back and do anything from the prior test? I doubt it, because we've got enough stuff here to do that we can pretty much go from where we stopped the prior test to now. And there will be a Bodie plot. There will be I'll give you the sheet. You don't have to bring the sheet with you. There will be a Bodie plot. There will be, one of each of the power, single-phase power and three-phase power. Nothing hard, but a problem like this problem, a problem like this problem, and I'll have those defined for you in the review. So I'll have that pretty well lined up on Tuesday. And I will not make it any more difficult than what I tell you. There's enough problems here that I can pick one of each, and you'll be practice those. You'll be okay. I will not surprise you. Okay, let's go back at the beginning of the session today. I basically went through a couple of things, and I think a few of you were not here, and I want to reiterate them again so that you understand that, hopefully you understand that we try to do the right thing for you. So this is the proposed sheet for you to have. Okay, so at the end of your 4 years here, you will be taking a bunch of courses, but we have 3 blocks for technical electives, 1, 2, and 3. And in those 3 electives, we have a bunch of courses that you can take. But you can take them a number of different ways, and one of them is you can take some mechanical courses, or you can take some electrical courses, and the electrical courses can vary. But we're going to have some courses under the mechatronics area, and we're going to call it mechatronics and robotics concentration. And there will be 3 mechanical courses. There will be the advanced, the Mech 2 course. And there will be a robotics course. And then there's some other courses that you can take as well in the area of not power, but wind energy and energy and that type of thing. So you have some choices in this thing, and you can pick any 3 of those and be in this mechatronics concentration, or you don't have to be, and you basically can do the same thing. But hopefully, if you do the mechatronics concentration, you will either pick some of the mechanical courses and this advanced Mech 2 and this robotics course, some combination of those. But I'm not going to preclude you from doing the energy one and calling it this. So basically, we're going to give you the list of courses, and if you want to call it under the mechatronics and robotics concentration, you can. If you don't want to call it that, but just pick courses out of this group of courses, you can as well. We also have a database course, which gives you a leg up there. My point is this, that we'll probably make these the area that if you take 3 of those, in this area, if you take 3 of these, you get this. Robotics, the mechatronics 2, or any of this 5 courses would satisfy this. But if you wanted to do some of this and this, we would probably do substitutions, but basically this would be outside of this concentration. That would be the way we're going to go. But we're going to bring this back. We're going to have this concentration. The reason being that we were told that you had to go to 15 hours with a concentration, but because we only have 3 courses in 12 hours, we can't go to 15. We had to drop them. But then we were told we are able to grandfather us in because we had the concentration already. So we're being grandfathered in. So we get to keep it. So that gives us an opportunity to do some things and keep the concentration, and we'll work out the details, but that's the plan that was decided yesterday. And I reviewed with you the syllabus also at the beginning of the class, and if you came in a little bit late, I went through the syllabus at the end and explained to you when we're going to do stuff and how we're going to do stuff, and that's basically it. Anybody have any questions? Hopefully everybody's okay. I know this transistor stuff is a little new and a little shaky because you haven't ever done it before. But if you think back into the thing that you're building, if you get that above 0.7 volts, it's like switching it on. If you think about it that way, you're in. If you don't think about it like that, it's like pure foo-foo dust. It's like magic, and you can't see it. But if you do see it as a switch, either it's on or it's off. If it's off, no current flows. If it's on, current flows. Then you can begin to master chapter 4. But you've got that lab to look at to say, oh, I see what's going on. If the value is above 0.7, and with that RC time constant coming down, when it gets to less than 0.7, the switch turns, and you see that. You actually see it. I know that's strange, but it's exactly what happens. Any questions? Any thoughts? Take care. We'll see you on Tuesday. I'll be up there and help you if you need help.